Hi, my name is Sinjin Sharma. I'm doing this presentation for my CFD 43R1 class for Dr. Patki, and this is a summary over the analysis of a swimmer's hand and arm in steady flow conditions using computational fluid dynamics. This study can be found in the Journal of Biomechanics, Volume 35, Issue 5, published on May of 2002, on pages 713 through 717. The authors are Barry Bixler and Scott Reimold. So for our introduction, this study focuses on using computational fluid dynamics to analyze the forces on a swimmer's hand and arm. To date, the propulsive forces on a swimmer's arm have been determined only through experimental testing, and the phenomenon of swimming propulsion is still not fully understood. Initial experiments would use a steady flow of air or water flowing past a model of a hand or arm. One early study in 1977 used a wind tunnel to determine the forces on a swimmer's hand and forearm, but the lift forces were two-dimensional and the third dimension was ignored. Another study looked at the 2D lift forces by flume testing a hand model supported by a rod. However, interference drag was not accounted for since it was assumed that the support rod encountered equal drag force whether the hand was attached to it or not. Another study measured force coefficients on a hand and arm by using a large experimental tow tank. Although the lift calculations performed were three-dimensional, the arm model ended up piercing the surface of the water, resulting in extra wave and ventilation drag. A 1990 and 1999 study concentrated on the unsteady flow and showed that acceleration and deceleration can significantly affect hand force coefficients. Both experiments accounted for fixture drag, however, the effects of interference for drag at the wrist were not considered. The issue with all these studies discussed above is that they were forced to choose between unwanted wave and ventilation drag or inaccurate interference drag. Using CFD eliminates this issue and has the advantage of showing detailed characteristics of fluid flow around the hand and arm. A study in 1996 provided the validity of using CFD for swimming analysis when it was used to show the effects of a flat circular plate through water. The results suggested that a 3D CFD analysis of an actual human form could provide useful information about swimming. And this paper serves to prove that 3D analysis using CFD can successfully be applied to swimming and show the hydrodynamic forces in steady flow conditions. So the approach. A CFD model was created based upon an adult male's right forearm and hand, with the palm facing downward and the thumb flush with the other fingers. Adaptive meshing was used to achieve the optimum mesh refinement, and the final mesh contained 215,000 cells. The angle between the model's x-axis and the flow direction was defined as the angle of attack. Angles of attack between negative 15 degrees and 195 degrees in maximum increments of 15 degrees were evaluated, with intermediate angles included in the analysis when they were needed. The water velocity in the experiment was held steady between 0.4 meters per second and 3 meters per second. The skin on the model was smooth or shaved, which was accomplished by setting the roughness height equal to 0. This eliminated a variable that could affect the results and fit with the practice of professional swimmers shaving their bodies before a major race. The tested water temperature was 22.6 degrees Celsius, and the tested water density was 996 kilograms per meter cubed. The viscosity was 8.571 times 10 to the negative 4 kilograms per meter second. The independent variables in this experiment were the angle of attack and the model and the fluid boundary velocity. The dependent variables were pressure and velocity of the fluid. Force was calculated after the experiment for the hand, arm, and the hand and arm combined using the equation shown on the screen. Ci is the corresponding force coefficients, Fi is the drag, lift, and axial forces, Rho is the fluid density, V is the steady free stream velocity of the fluid relative to the hand and arm, and A is the maximum projected area of the hand, arm, or the hand-arm combination, depending on what we're looking at. So the results. The force coefficients were measured using CFD and calculated as a function of angle of attack. They showed They showed expected trends that closely resembled the data collected in the previous studies that we discussed in the introduction. Arm drag was essentially constant with a CD of 0.65, and the arm 2D lift was 0. The drag on the hand was the smallest near angles of attack of 0 degrees and 180 degrees and reached a maximum of the CD equaling 1.15 at 95 degrees. Hand 2D lift was 0 at 95 degrees and peaked near 55 degrees and 140 degrees, with more lift generated when the pinky finger was leading than when the thumb was leading the motion. Axial coefficients were large for the arm at all the angles of attack, and large for the hand near angles of attack of around 90 degrees. All force coefficients were constant for the flow velocities between 1 meter per second and 3 meters per second for a specified angle of attack. As flow velocity was decreased from 1 meters per second to 0.4 meters per second, the axial and 2D lift coefficients remained constant, while the drag coefficient began to slightly increase. Flow separation occurred at all angles of attack and all fluid velocity values. So the conclusion. There's some slight deviation between the values of the CFD data collected here and previous conducted experiments. However, the trend remains the same, and the value difference is likely due to factors outside of the control of previous experiments, while the CFD model test was conducted in a perfectly controlled environment. As mentioned in the results section, it was noted that the flow separation occurred at all angles of attack and at all fluid velocity values. This indicates that Bernoulli's equation should not be used to explain the lift forces that swimmers generate with their hands, since Bernoulli's equation is applicable only to ideal flow. The results of this specific study were limited to steady flow into sweepback angles of 0 degrees. Because a symmetry plane at the end of the forearm was used, errors resulting from wave, ventilation, or interference drag were prevented. In practice, swimmers do not move their hands and arms in a steady direction and velocity, and previous studies have shown that unsteady and steady motion can give different results. The purpose of this experiment was to show that CFD modeling could be used to show the forces that act upon a swimmer's arm, which it successfully did. The study showed that the goal of evaluating complete arm strokes and designing the optimal swimming stroke pattern is indeed obtainable by CFD methods. That is the end of my presentation. Thank you very much.